introduction. So yeah, I'll be talking about the mechanized semantics for gated static single assignment and its implementation in CompCertSSA. So first, I'll quickly go over a refresher on SSA itself. So SSA was introduced in the late 80s, and it's now widely adopted in various compilers. And it's mainly used as a middle end where various optimizations are done on it. And so the main characteristic of SSA is that each variable has a unique definition point in the control flow graph which simplifies various analyses. So for straight line code, the SSA generation is quite straightforward. So every redefinition of a variable we actually instead assign to a new version of that variable, and then in subsequent code we'll have to rename uses of the variable to use this new version. But we run into a problem when we have a control flow join point, because we're actually not certain which k we're going to assign to m. And so in SSA, the way this is solved is by introducing a phi instruction which will select the right value of k, so either k1 or k2, depending on where the control flow came from, and so basically in which branch we went into at runtime. And so the main, yeah, exactly. And so the phi function will execute just before the m assignment, and we can then use k3 in the later code to refer to either k1 or k2 based on how we executed the code. So the main strength of SSA is that it's a nice CFG-based control flow graph-based representation, and so we can have simple operational semantics for it. And these phi instructions and SSA in general captures the def use dependencies very nicely. So one weakness of SSA, though, is that the semantics of phi instructions themselves are a bit weird. They're actually not very local to the current execution context. To execute a phi instruction, you have to actually look at where the control flow came from to make the right choice. And so this complicates this. If you want to have a pure data flow view of your program, it's not quite possible because you always because the phi instructions don't really encode this data flow information, and you can't just execute phi instructions based on just the program context. So gated SSA is an extension to SSA, which aims to address this weakness. And so the main idea is to translate these phi instructions into new gating instructions, which encode all the data dependency information required to just execute locally with the program context and pick the right variable at runtime during the execution. And so the main structure of a gated SSA is that we introduce these new gating functions. So for example, when we have, so the, as the base of gated SSA, we have two new functions or two new gating instructions that will replace all the phi instructions. So for simple join points, where we'll have a phi instruction in the SSA code, the gated SSA will have this gamma function, which pairs each register in the phi instruction with a predicate that should evaluate to true when we should pick that register. And so it means that we can just execute this gamma, locally with the execution context and pick the right variable. However, there's a small problem with loop headers where we actually can't find an adequate predicate to select the right register. And so in this case, gated SSA just introduces this new instruction which acts exactly like the phi instruction. And so on loop entry, you'll pick R0, and then for every iteration, you'll pick R1. And it has the same semantics as phi instructions. However, we have one additional node that we add to the graph, and this is an eta instruction, and it's paired to every mu instruction. So these eta instructions are added to loop exit points. And the main purpose is to separate loop carried variables that are in the mu from being used outside of the loop. And so we can then gate them with this predicate P that should encode a condition which will be true whenever you exit the loop. And so the main problem, though, with gated SSA is it's been used a fair amount in the past, but there are always different definitions of gated SSA, and each comes with its own notion of these gates or dependencies, and normally the description of GSA is quite informal. And so our contributions are to describe a formal specification, and in this work, a control flow based semantics for gated SSA. However, we put our focus on the control flow independent semantics of the phi instruction replacements, in particular the gamma and the eta instructions, which have those predicates that make them more local. And so then we also describe an implementation and proof in CompCertSSA, which is an extension to CompCert with an SSA middle end. So now I'll just go over an example of a translation from SSA to GSA to get an idea of what that looks like. So we'll be working with this kind of control flow graph. So this is an RTL, which is the standard intermediate, one of the intermediate languages of CompCert. And here the structure is relatively simple. We have one loop and then a lot of branching inside of the loop. And so we use CompCertSSA to then generate an SSA version of that control flow graph. The first thing to notice is we've actually changed the structure a bit. We've added a lot of NOP instructions. This is to normalize the control flow graph. And then now all the variable assignments are unique. We've versioned all the variables. And we now have these phi functions that are placed at both the join points, at the loop header and the bottom of the combination of all these if branches. And these will make the correct selection of the version of that variable. And so then we take this graph and we translate it to our gated SSA intermediate language. And so the first thing to notice is that the structure of the graph hasn't changed, but we have actually renamed some variables because we've inserted this new eta node, which is the node that separates kind of the loop carried variables from use outside. And so now this is gated by the negation of the loop condition. So that is true whenever you exit the loop. And we rename every use of x1 to x6 outside of the loop. Then at the loop headers, we've just changed the phi instructions to mu instructions. And at the bottom, where it's not a loop header, just a normal join point, we've inserted a gamma instruction, which now pairs each register with these predicates. And so these predicates are syntactic elements in the control flow graph. And so they can just be executed locally to make the selection of x2, x3, x4. You don't need to look at the incoming control flow edge anymore. Oh, okay. So the main way we generate these predicates is using this single source Tarjan's algorithm as a solution to the single source path extraction problem. And so what this problem says is that for every vertex v in a graph G, we want to find a regular expression which characterizes the path from a source S to all the v's in the graph. And so the way we can use that then is by running this algorithm for some source, and I'll show kind of what source we use. And we then get these path expressions, which are regexes, and we can easily actually translate them to predicates by converting edges to syntactic conditions. And so I'll give an example of this to make the structure a bit more clear. But as a high-level overview, for example, for a gamma instruction, we'll have some source, which in this case is the immediate dominator of the gamma. So one node where we know kind of all the points, just the immediate dominator of the gamma. just so that we kind of get this triangular control flow graph shape, which converges on the gamma. And we then run the single source path expression Tarjan's algorithm between S and all the predecessors of this gamma node. And these will then give all the predicates that we should pair with every register in that original phi function. So, for example, for the first one, the PSV1 will be a predicate that characterizes the paths between S and V1 and should therefore be true whenever you reach V1. And so that's the predicate you should use to select the variable. So now I'll kind of explain the proof, but also give a better example of what these predicates look like. So the main thing is that we actually haven't formalized this algorithm, Tarjan's algorithm, as a solution to the path expression problem. And so instead, we want to validate the predicates in those gamma instructions after the fact. And so the main issue with this is that if we want to reason about the evaluation of these predicates at the gamma point, it's quite a global and dynamic property, because we need to be able to say that this predicate characterizes all the paths between the initial point and the predecessor that should then pick that, mean that you pick that register. And so we have to reason about all possible, the one path we execute, but also a bunch of paths we never touch, and prove that those will mean that predicates evaluate to false, for example, for all the other registers we don't want to pick. And so the key idea in which, for how we can solve this is by using small local correctness rules about predicates for every node in the graph, so not just for gamma nodes. And we use these local correctness rules to build up, to slowly build up a proof about the evaluation of the predicates. And so essentially we have this, we have two local kind of correctness properties that should imply this global validity property about the execution of those predicates. And so in the next slides, I'll only be really talking about the coherence property. I won't really mention the mutual independence property, but we use those two together. So okay, now I'll give a more detailed kind of look at what these predicates look like. So this is just an extract from the control flow graph that we had before. And so our source will now be node 4. That's kind of where we start to branch off. And then our final node is node 12, where we then want to turn this phi function into the gamma function. And so we now want to generate these predicates using the Tarjan's algorithm. And so it will generate these predicates for us. For example, at node 4, the path between 4 and 4 will always be there locally. And so we don't really need a predicate that characterizes the path. So we just set it to true. But then as we continue, we kind of build up these predicates. And for example, if you take the condition C4, 5, so x1 will be less than 9, so then the predicate that characterizes that path will be associated with that condition. And so we continue like that down the, using this Tarjan's algorithm. And finally, it might generate, so it just generates kind of opaque predicates for us. So at the end, it might set P412 to just be true. And that's actually because all paths from 4 will eventually reach the node 12. And so again, we don't need a predicate that characterizes that path. And so now to talk about the coherence property, we don't actually have to look at the code itself anymore. We just have to talk about these predicates. And in addition to that, this was just an example of like what these predicates could look like, but in practice, they're opaque to us. We just generate them externally, and so we don't really know what they look like structurally. And so we now want to come up with a local property that will help us prove this global evaluation property. And so we can basically come up with this a coherence property that says that if you're at a node, for every node, for example, in this case, the node 5, we want to show that this node will be true whenever you were at 4, so whenever 4 holds, and you took this C45 condition. And so this is now a small static property that, for example, I'll show later, but we can prove using an SMT solver. And so the way we use this in the proof is, I won't really go into the simulation diagrams and the high-level proof, but at a more local level, we end up with this kind of invariant in our state matching in the simulation diagram, which says that kind of, this is a simplified version, but like that all predicates 4 to I should evaluate to true. And so then we can use this coherence property to show that when we reach 5, because we can assume that 4 evaluates to true and that we've picked this edge, then we can show that this P45 will also evaluate to true. And so we now know that P45 evaluates to true. And once we then reach the node 12, so we then have to execute this phi function, which now will be a gamma function. And we know that this one will execute to true. And so we can place that with the x2 variable, and then correctly, we know that we'll then pick the same value as the phi instruction. So that's kind of just an example of, at a low level, how the proof works. And so now we've got these small kind of predicates that we want to prove true for every node in the graph. So this is just an example for node 5, but we'll prove kind of these coherence properties for every node in the graph. And we can do that by using an SMT solver and encoding this property as a 3-valued logic formula. And so we actually need 3-valued logic because the conditions inside predicates are syntactic, and there might be parts that we don't know how to evaluate yet, for example. And so in particular, we use this Lukasiewicz 3-valued logic just so that we can have some tautologies, because by default, you can always evaluate these 3-valued logic formulas to just nothing. So we then, the way we actually integrate this SMT check in our proof is by using SMTCoc and Verity, an SMT solver, to obtain validated SMT, a validated SMT check, which we can then use directly in our Coq proof. So as a quick summary, so we defined the syntax and semantics of gated SSA in the CompCert framework, and proved the generation of gated SSA correct. And so we did that by using 2 local properties, coherence and mutual independence, to prove a kind of global validity property of our predicates that we eventually put in our gamma instructions. So some of the limitations of our current implementation is that our conditions inside of predicates don't actually support conditions that depend on memory. And so in CompCert, there are actually a few conditions that do depend on memory, like pointer equality checks. And so for now, we don't really support them, and we need a more global validity property about the C program to be able to prove this. And the predicate validation that we do is quite slow at the moment because we're using this validated SMT solver approach, and so we have to use a relatively old version of Verity, which handles some formulas badly. So some future work we'd like to work on is develop a pure data flow semantics for GSA. Currently, we're still in a control flow graph, and this would help, for example, to target various kind of data flow languages. One could just be hardware. Another future work would be to prove, which we've started working on a bit, is to actually prove and formalize this Tarjan's algorithm for the predicate generation, and this would speed up the compiler by a lot. And the interesting thing to note is that this actually would wouldn't have to change the proof much, because we could just prove our coherence and mutual independence using this formalization. And finally, we just like some stronger properties about GSA. Currently, we just have correctness of generation, but there are some more structural properties we'd like to prove at some point. So thank you.
Thank you. We have time for maybe one quick question before we go to break.
So, yeah, it sure, maybe it's a dumb question, so maybe I shouldn't have used the one question. It sure feels like this local kind of prove these local properties and verify, that you have the correct path. It just feels like a strongest post condition calculus. Is there an analogy there, or no?
I haven't thought about that strongly yet. I would guess yes, but
okay. And here's I'm going to slip one in by cheating. In retrospect, should you have started by formalizing Tarjan's algorithm instead of doing this cool but
started by it? Yeah, so that was our first idea, was to formalize Tarjan's algorithm.
But now that you've done the other thing, do you think you should have started with the Tarjan algorithm?
Oh no, so we did start with that, and we realized that the proof of the algorithm, it was much more complicated than we thought it was.
Okay.
So, yeah, there are a bunch of properties that just don't translate nicely into a mechanical proof. Yeah.
Cool. Thanks.
All right, I guess we'll wrap up. But thanks again